Welcome back to Cosmic Earth, your favorite spot for space and physics. Today we are tackling a question that might actually keep you up at night. Why does anything in our universe actually exist instead of just empty space? It turns out that physics says we should not be here at all. Let us travel back about 13.8 billion years to the very beginning. According to our best cosmological models, the Big Bang created equal amounts of matter and antimatter. This means for every single particle of normal matter, an identical antimatter twin was also born. But if that is true, they should have completely destroyed each other instantly. To understand this cosmic puzzle, we need to look at what antimatter actually is. In 1928, physicist Paul Dirac wrote down an equation that changed everything. He realized that every subatomic particle has an opposite version of itself with a reversed electrical charge. For example, an electron has a positive twin called a positron. Here's the thing about these twins. When a matter particle meets its antimatter counterpart, they instantly destroy each other in a flash of pure energy. This process is called annihilation, and it is the most efficient energy release in the known universe. If you put a gram of matter and antimatter together, it would unleash an explosion like a nuclear bomb. Now picture the early universe just a fraction of a second after the Big Bang. It was an incredibly hot, dense soup of particles and antiparticles colliding constantly. Every single pair was destroying each other and turning back into high-energy light. If the symmetry was perfect, the universe today would be nothing but a cold sea of radiation. But obviously, that did not happen because we are standing here today. Somehow, a tiny fraction of normal matter managed to survive this massive cosmic cleanup. For every 1 billion particles of antimatter, there were 1,000,000,001 particles of normal matter. That tiny, single extra particle is what built all the stars, planets, and even us. So how did this tiny imbalance happen in the first place? In 1967, a brilliant Soviet physicist named Andrei Sakharov proposed 3 essential conditions. He argued that the universe must have deviated from its perfect balance during its rapid expansion phase. Without these 3 conditions, our universe would have remained a lifeless void of light. One of Sakharov's key conditions is called charge parity violation, or CP violation for short. This is just a fancy way of saying that nature treats matter and antimatter slightly differently. It means that certain physical laws do not apply in the exact same way to antiparticles. This tiny difference is the key to why matter eventually won the cosmic war. Scientists actually proved that CP violation exists in the real world back in 1964. James Cronin and Val Fitch studied subatomic particles called neutral kaons at the Brookhaven National Laboratory. They discovered that these particles decay in a way that slightly favors normal matter over antimatter. This groundbreaking discovery earned them the Nobel Prize in Physics in 1980. But here's the catch that keeps physicists working late at night. The amount of CP violation we have observed in nature so far is way too small. It only explains a tiny fraction of the matter we see in the cosmos today. There must be some other, much larger source of asymmetry that we have not found yet. To find this missing piece, scientists are using the largest machine ever built by humans. The Large Hadron Collider at CERN smashed protons together at nearly the speed of light. These high-energy collisions recreate the extreme conditions of the universe just after the Big Bang. By studying the debris, researchers hope to spot new particles that behave unexpectedly. A specific part of this giant machine is dedicated entirely to this mystery. It is called the LHCb experiment, and it focuses on studying beauty quarks. These exotic particles are highly sensitive to subtle differences between matter and antimatter. In recent years, researchers here have made incredibly precise measurements of these differences. Some physicists believe the answer might lie with the most ghost-like particles in the universe. Neutrinos are nearly massless particles that can pass through solid lead without touching anything. They come in 3 different types and can spontaneously morph into one another. Scientists believe that neutrinos might violate CP symmetry much more than other particles. In 2020, an international team working on the T2K experiment in Japan found exciting clues. They shot beams of neutrinos and antineutrinos across hundreds of miles of solid Earth. Their data strongly suggested that neutrinos behave differently than their antimatter counterparts. This could be the breakthrough we need to explain our existence. But what if the antimatter did not actually destroy itself in the early universe? What if it just got separated and pushed to the far edges of space? In this scenario, there could be entire galaxies made of antimatter floating out there. These anti-galaxies would look completely identical to normal galaxies from our telescopes. However, this theory has a major problem that makes it highly unlikely. If antimatter galaxies existed, they would eventually drift near normal matter galaxies. The borders between these regions would be hot zones of constant, violent annihilation. We would see massive amounts of high-energy gamma rays coming from these cosmic boundaries. To search for any stray antimatter from deep space, scientists built a special detector. The Alpha Magnetic Spectrometer was installed on the International Space Station in 2011. It has spent over a decade scanning cosmic rays for heavy anti-helium nuclei. If it finds even one, it would prove that antimatter stars exist somewhere. So far, the results from space have been incredibly quiet. The detector has analyzed billions of cosmic ray events, but found no clear evidence of complex antimatter. It seems that the observable universe is indeed almost entirely made of normal matter. This confirms that the asymmetry is a universal feature, not just a local one. Since we cannot find antimatter in space, we have to make it ourselves to study it. The Antimatter Factory at CERN is the only place in the world that can do this. Scientists there use decelerators to slow down antiprotons so they can be studied. It is an incredibly delicate process that requires extreme precision and patience. Trapping antimatter is one of the hardest challenges in modern physics. Because it annihilates upon touching normal matter, you cannot store it in a normal container. Instead, scientists use complex magnetic and electric fields to suspend antiprotons in a vacuum. The Alpha collaboration at CERN has successfully trapped antihydrogen atoms for several weeks. One of the most basic questions scientists wanted to answer was how gravity affects antimatter. Does it fall down like normal matter, or does it fall up? In late 2023, the Alpha experiment published their groundbreaking results. They confirmed that antihydrogen falls downward under gravity at the exact same rate as normal hydrogen. This result was a massive victory for Albert Einstein's theory of general relativity. His weak equivalence principle states that all mass should react to gravity in the exact same way. If antimatter had fallen upward, it would have turned our understanding of gravity upside down. Once again, Einstein's predictions held up under the most extreme tests. Scientists also compare the light spectrum emitted by normal hydrogen and antihydrogen. According to the laws of physics, they should absorb and emit the exact same colors of light. So far, the measurements have shown that their spectral lines match with incredible precision. This suggests that the internal structure of antimatter is a perfect mirror image of matter. Because it's so difficult to produce and trap, antimatter is the most expensive substance on Earth. A single gram of positrons would cost an estimated $25 billion to make. It would also take millions of years of continuous production at our current rate to make that much. For now, we can only work with tiny fractions of a gram. Despite the high cost, antimatter already has practical uses in our daily lives. Positron emission tomography, or PET scans, are used in hospitals every day to detect diseases like cancer. These machines use radioactive isotopes that emit positrons inside the patient's body. When these positrons annihilate with nearby electrons, they produce clear images of our internal organs. Looking further ahead, antimatter could become the ultimate rocket fuel for interstellar travel. An antimatter engine would be far more efficient than any chemical or nuclear rocket we have today. Just a tiny fraction of a gram could power a spacecraft to the outer planets in weeks. However, we are still many decades away from building such technology. Let us take a step back and look at the big picture of our cosmos. The fact that we exist means there is a deep flaw in the symmetry of physics. This cosmic glitch is the only reason stars could ignite and life could eventually evolve. We are essentially made of the leftover scraps of a massive primordial battle. So, what is the ultimate takeaway from this cosmic detective story? We know that the Big Bang should have created a perfectly balanced, empty universe. We know that a tiny 1 in a billion asymmetry saved us from total annihilation, but we still do not fully understand the exact mechanism that caused this saving grace. The search for this answer continues to drive the frontier of modern physics. New experiments at CERN, deep underground neutrino detectors, and space telescopes are searching for clues. Every day, we get a little bit closer to solving this ultimate origin story. It is a reminder of how much we still have to learn about our universe. Thank you so much for joining us on this journey through the cosmic anomaly. If you enjoyed learning about the Antimatter Mystery, please hit that like button and share this video with your friends. Do not forget to subscribe to Cosmic Earth for more deep dives into the secrets of the cosmos. Let us know in the comments what mind-bending topic we should explore next.